So was it interesting that the previous one-dimensional cell automata? And were you able, was it interesting enough to do a multiple more further iterations? There was someone who were interested in that rule and cell automata transition rule, and that person was being called Stefan Wolfram. His name was Stefan Wolfram, and actually he is a creator, okay, inventor of the Mathematica, a software that you might already heard of, okay. So he was interested in such kind of cell automata progress, and that rule, which we did earlier in that one-dimensional binary cell automata rule, was created by Stefan Wolfram in 1983. It's been called Rule 30. Then that means that you will question, is there Rule 1, Rule 2, Rule 3, Rule 4? Of course there are. And that particular transition rule was Rule 30. And if you progress that Rule 30, it will create this type of some interesting, some complex pattern. Do we see these patterns in the real world? Yes, we can see these patterns in the real world that's hidden here. Okay, this shell piece is the surface, like the outer shell, is exhibiting very similar patterns that we recover from the Rule 30. Similar? To me, somehow similar to each other. Okay? Then we can question, so, okay, it could be coincident. However, can we provide more interesting rule that imitates the real world phenomenon that we are interested in? Not the shell piece, the shell pattern, okay? So by the way, the Wolfram classified those transition rules into four classes, class 1, 2, 3, and 4. Okay, and those four different classes of rules showed different mechanism or the result. And class 1 was very stable. Okay, it does not show many of those changes. And class 2 was stable, but sometimes some oscillation, however, soon being stabilized. Okay, and class 3 was really random shape, random pattern. Does not produce any types of this. Sometimes some big triangle, these types, not these types of patterns, but real random patterns, class 3. However, class 4 was most interesting one, which showed complex and interesting patterns. Okay, eventually evolved to class 2, which are being very stable at the end. Okay, it was converging to the stable moment, right? And this is a classic example of what? Class 4. So it turns out that some cell automata rules are reproducing the natural patterns, as we can see here, or some of our own artificial, like human-created patterns. All right, the urban growth. So this is an urban growth model, which is being modeled by its own customized cell automata rule. So it means that each of these urban area has been modeled as being modeled as a cell, small cells. And that each of these cells has state and also its own transition rules. And one of the most famous model in that urban growth model is being called SLUICE model, for example. SLUICE is an acronym of slope, land use, and excluded development, and urban area already being developed. Transportation affects something in terms of urban growth. And hillside means that if there is a cliff, there will be no real growth in it. And then those slope, land use, excluded urban transportation and hillside all together. These are the factors and states of cellular automata model here that imitating the urban development. Like we developed shellfish shell pattern development with Rule 30. Of course, it's not going to be a Rule 30. It will be being more complex rule. However, there are rules to create such kind of artificial patterns that we see and being interested in it. And then people start asking questions, how to come up with those rules and how to formally reference those rules. So now we are going to turn ourselves to the formalism aspect. Before we go further on the formalism side, I wanted to show you the classification of those cellular automata rules suggested by the Wolfram. So here, this is class 1, which is very stable. It has nothing in it, so it means that it's being stable. Or some stable and oscillation case, so some oscillating or random noise are being there. However, soon it's being stabilized, so it doesn't show that much changes. Okay? And class 3 is a pseudo-random, real random case, and chaotic case. However, 4 is the, okay, it shows more, like, has some patterns, complex patterns in it compared to class 3. And then these patterns will evolve to the class 2 later.